plate tectonics on the macro scale and their efficient treatment. He has, to his credit, published 34 peer-reviewed articles in highly reputed journals in internationally acclaimed journals, and has also published over 20 of them in the last 2 years. Besides, Dr. Franz Balmer has also published 29 proceeding papers apart from 2 book chapters. With this brief introduction, I would like to now hand over the platform to Dr. Franz Balmer, the group leader from the Institute of General Mechanics, RWTH and University, Germany. Over to you, sir. Thank you very much.
Thank you very much for the kind introduction, Mr. Chairman, and all for presenting the biography. For all the things that was in the biography, I will talk today about the last part, or let's say the last little part of the whole processes I'm researching on, which is the efficient treatment in nonlinear structural dynamics or nonlinear systems. Okay, and I also want to thank also Professor Bernd Markert and of course Sandy Patil that he lets me speak in front of the audience. Okay, so the title is Model Order Reduction and Efficient Metamodeling in Structural Mechanics. What does it mean? Model order reduction means generally that we reduce models in a mathematical way, and efficient metamodeling, I put this also into the equation because there are certain mathematical procedures as neural networks that do not fall into the framework, into the mathematical framework of classical model order reduction. Okay, so let's go into the topic. So this is the general. We have limited time, so I cannot talk to you about everything, but this is the general schedule of today's lecture. Firstly, we'll talk about the problem formulation and the motivation of model order reduction, or what problems do we have in structural dynamics and what are the obvious problems. Then I will talk about the space-time solution ansatz. So this is one ansatz, one ansatz to deal with this problem. So which will be the first main ansatz in this talk. Secondly, then I will talk about a quasi-static space-time solution ansatz for nonlinear problems. And then I will talk about an elastodynamic space-time solution ansatz for linear problems. And in the end, I also want to give an insight into neural network enhanced meta modeling, where we use it, amongst others, where we use it in structural dynamics. And we use it also in other things, but as already said, we have only, let's say, half an hour to 45 minutes here. Okay, then let's start with the problem formulation and motivation. In the left corner, you see a little benchmark example that's quite simple. In the end, it's then not that simple because you need numerical tools to solve this problem. It's, for example, frame structure, discretized by finite elements, which makes sense. And the frame structure behaves nonlinear. That's necessary because we know as engineers, we know that structures shortly before the break behave highly nonlinear. So nonlinearities are somehow linked to the prediction of structural failure itself, which demands us to create systems or to create algorithms that deal with nonlinear systems, and that in an efficient way. So if you look at the next picture beside the, I hope you see my mouse, so here you have the structure, then you have here a certain transient excitation. This transient excitation demands a stepwise, if you want to say incremental, I say incremental now, stepwise incremental procedure anyway. So we start from a time instant t0. That's what we do. That's classical mechanics. We start from a time instant t0, and then we go through time, and there's the structure responses in time. There's certain vibrations and so on, until we were at the time instant where we want, and then we stop the calculation, and then we evaluate what we did. Upside okay. We evaluated what we did. Here we tend, or what we do is we do not only a spatial discretization, we also perform temporal discretizations, which means we divide the whole timeline into certain discrete time instants, t0 to t, where ti, for example, is the ith time instant. Now, yeah, and then we try to define the dynamic equilibrium of the nonlinear system at every time instant. That's actually the first basic rule of time integration, is that the time that the equation is fulfilled at certain time time instance, which you have here. So we have equilibrium at time instant e, that mu e double dot plus c u e dot plus f internal is f. Okay, this is the first big thing. What we do is, and that's the clue, what we do is we're starting at a time instant t0. Then we have a certain procedure. Whatever we do, it's incremental. Is it implicit or explicit? We start at a certain time instant, and then we go over to the next time instant. Then we have our next values and our next start for the next time instant, and we go over to the next instant, and then we go to the next time instant. Luckily, we have computers who do this for us. So we go step by step, incremental in time, and this is along generally in nonlinear mechanics, as also in for high-dimensional systems. This is either implicit or explicit, whatever you use. It's a long path until you finally reach where you say, okay, I'm stopping my algorithm now, and then I start again. Okay. Let's look at the static problem. Let's just look at the static problem for a beginning. It's just a reminder for you, or for other people, it's very nice to remind you again how to solve such a problem. We have static equilibrium, which demands an iterative solution procedure. So we have equilibrium, which means the internal forces in the system are equal to the external forces, is what this says. You can reformulate the whole thing in an iterative incremental way, that you say that a tangential stiffness matrix times an incremental displacement is equal to a residual force, so F external minus F internal. Okay, the residual force. And then you proceed again from u to the next time step. So ui is ui minus 1 plus delta u. Okay, then let's look what happens. Now we are starting at ui0. Then we calculate a certain tangential stiffness matrix, which you see in K1J, and then you calculate the residual, and then you can solve this problem. K times delta U is the residual. This equation is going to be solved here. Okay, so after solving this equation, you have to update the displacement using this. Okay, then you go forward, because the residual is still not equal to 0. So we calculate the internal force again, which means solve the finite element problem according to stresses and strains. And then you calculate the second increment again, and you add it up to your increment. Then we do it again. We again solve the finite element problem going through the material law and all the things, and calculate the next linear system of equation, the next linear equation systems. system, and the next. And so on and so on and so on until you see already there is a certain convergence behavior, which we do, so that we in the end find our displacement UI. Yeah. So what these algorithms actually are, because so actually in nonlinear mechanics, we're actually not solving nonlinear systems, nonlinear equations, we're solving linear equations in an iterative way, which means with all the problems that come with it, with certain LU decompositions, and so that we don't have to invert the stiffness matrix, whatever, there are certain things that are computationally expensive and seem to be unavoidable. So what are we doing is we go from one time step you see in blue to the next time step. Is from ti minus 1 to ti, or you can also say ti plus until ti plus 1, which is the same, okay? And then you you have certain starting conditions, and then you solve the iterative, the nonlinear system, you update, you calculate the finite element system, so the stresses and strains, so the internal force that refers to the stresses and strains, and then you calculate, let's say, if you want to, a tangential stiffness matrix, which is not always necessary. You can also do it differently. So what does this algorithm mean? It's computationally expensive. There are a lot of things that are computationally expensive. The only thing that's not computationally expensive is the simple addition of vectors, which is done in a fractional amount of time, but everything else is computationally expensive if system gets large, or when system gets large, because they do, unfortunately. Yeah. So this was the static problem. So I give you a little insight into the dynamic problem as well. I think you know this already. So this is the equation. You have to let's call it dynamic equilibrium, because I mean, we all know Newton says this is not equilibrium system, and D'Alembert says it's equilibrium. So we'll say it's a I say it's dynamic equilibrium. So we have forces of inertia as well here, and damping forces, and this is the explicit formulation of the equation of motion. You can also rewrite this in an implicit formulation of the equation of motion, because today we're talking about implicit methods and not explicit methods. So I want to emphasize more about the implicit equation, which means m times u double plus t times u dot, k delta u, which the tangential stiffness matrix is a residual, which is nothing else than an extension of the static equation above with by the forces of inertia and the damping forces. So the nonlinearity is generally only in the material in our course or in our lecture here. Just to remind you, what we're doing is we have certain quantities, vectorial quantities at time instant ti minus 1, and we have certain vectorial quantities at the time instance ti. Okay, and then we go from this to this, and in between, and now we come to the next point of numerical integration. Oops. We come to the next point of numerical integration, which says that you don't only have fixed time instants. At fixed time instants, you know you have equilibrium. In between those time instants, you need polynomial interpolations. Okay. For example, the most simple polynomial interpolation is Euler, who uses a line, or central differences using a second order. We have used the Newmark method, which is also kind of a second order approximation, which means we have the system fixed at certain time instants, and we have the two Newmark equations, y2, because we have three unknowns in an equation. In a numerically, we have three unknowns, which is acceleration, velocity, and displacement. Okay, so we have two Newmark ansatz functions and the incremental the incremental set of equations of motion. Let me say it just now, and then later you see why I say incremental. So this is the problem we have. We have to go step by step, and things are expensive because of the reasons I've told you before. So next thing in our schedule is how to deal with that. And there are a gazillion things how to deal with this, and all for certain applications, and all have the advantages and disadvantages. And I'll show you now one method where I think, or where I made the experience in the last years, that it has the least number of disadvantages that you can have when you use mode order reduction, okay? Which is a space-time solution ansatz. What is the general idea? Okay, the general idea is space-time solution ansatz. You have, everybody knows that you have a solution, you have certain displacement function at discrete time instance. We defined this before. At this discrete time instance, we have dynamic or static equilibrium. And this can be written as a matrix if you want to. I mean, it is convenient to write the whole thing as a matrix. Or let's even generalize that a little bit. Let's say an object of second order. Let's say a vector is an object of first order and the scalar is an object of order 0. And I'm not saying tensor because, yeah, an object of the second order. And now imagine you have, and you don't, it doesn't matter where you have it from now. You have a certain convenient mode pattern and a certain time function at which this convenient mode pattern moves at. Okay, so this convenient mode pattern is represented in a discrete framework by a vector, and this convenient time pattern is represented also by a vector. So let's put it this way: you have a space vector and you have a time vector. Let's put it this way: space vector and a time vector. So what you're getting here is the dyadic product of a space vector with a time vector is a matrix. Okay? So you can say, I mean, a bold statement, I say that the displacement matrix U, which let's say is the space-time solution, is the solution at different times instance, is represented by a dyadic product of a space vector times a time vector. Of course, the challenge is to find this space or time vector. Okay? So, I'll go back. What I want to say is, if you have a space vector and a time vector, if you have the dyadic product of only one vector pair, most probably you have already, if you get already think, this will not be enough to describe complex motion forms. Let's see, a structure vibrates in several modes, then these are several linearly independent patterns. So only one pattern will not be enough. But I say, you see here, this is the approximate sign. So let me go forward. So we need perhaps another pattern. Whatever it looks like and how we calculate it, we don't know yet. And perhaps we need another pattern to describe the space-time solution function. Say solution function represented as a matrix. Of course, this whole formulation exists also continuously. It's just a little bit more complex to, I think in matrices that's very nice to explain. Right? Then if you're interested in the continuous framework, there's a paper in published in Computational Mechanics only shortly by me and other co-workers. Yeah, and if you put this in a mathematical framework, you see immediately that a certain function u is approximately an enrichment of I is equal to 1 and m USI times UTI, and then you have represented your matrix. So this is the general idea. The approximate sign I'm not 100% happy with. On the one side, mathematically, if you have a discrete framework, there is a finite sum of these space-time enrichments that ensures an equal sign here. Okay? However, as we use more order reduction, we don't want the sum to be that large. So we use an m for perhaps a number that's much smaller than the really necessary number to have an equal sign here, okay? So we will find a number m that's much smaller that gives you the solution in very small, in very fast, okay? So this is our certain magic formula in space-time integration. So this is the space-time decomposition. And now look at a certain problem. Now I have a continuous framework for you. Let's look at the cantilever. This is a cantilever beam, and we have a force F of t at the end. This is, let's forget finite elements and everything. This is just a continuous framework. You can calculate it continuously. There are certain answers function, yeah. And you have, this is a certain body omega, the body here, you have it here, okay. And then you see this axis here, that's also in bold, that's the time axis. And if you look at the certain movement of this cantilever beam, which is here obviously some kind of oscillation, okay, then you have oscillation here, then you have in blue a function that is obviously a function that's parallel to the time axis. And then I tell you in red I have a function that's obviously a function that's parallel to the space axis here. Okay. And you will see that with these two functions, it's a continuous framework, so it's functions and not vectors here. Indeed, with these two functions, you could represent the solution of the systems quite well already. So the idea is perhaps you don't need that many functions in space and time, or let's say function pairs. Oops, no, it also goes in itself. Why? Certain function pairs that represent the whole system for you. So this is the body omega. So the idea is that if you look at that, conventionally we go from t0 to time t0 to t1, and we calculate the space vectors incrementally in time. And within these little time instants, we even need expensive iterations. So let's say we have 2000 time steps, which is nothing special, it's just normal. And you have 2000 time steps times, I don't know, for 20, 30, 40 iterations. There is a lot of processes with a lot of big matrices and so on. The idea is, again, to use the whole space-time problem. And in sums, as you see, in a sum, you sum up and not incrementally, but iteratively build up the whole solution of the problem. So this is the conventional method, which is incremental. This is a non-incremental, which is space-time. This is one non-incremental strategy, okay? Good. So this was the general idea without a mathematical framework. You can imagine mathematically, it's not, you have to explain a lot of things, and it's not written in such a nice way and illustratively, okay? Let's now talk about one application of the whole thing, one nonlinear application, which typical nonlinearity is elastoplasticity. In engineering, you need it. Steel behaves elastoplastic. A lot of materials do. So elastoplasticity is kind of a benchmark examples for these numerical methods. Okay. In order to deal with this problem, we have to produce space-time equivalence of the equation you saw before, which is static equilibrium. Static equilibrium, just to remind you, was F internal is equal to F external. Or in an iterative way, incremental way, K times K tangential times delta U is the residual. That's the incremental equation. And these equations, or this equation of equilibrium, has to be transformed into spacetime. So you have a certain matrix U, okay? And then we normally have increments, so you can divide this into not increments in time, but space-time increments delta U. And after these space-time increments, you can say every space-time increment I define, or whoever wants to do that defines that the space-time increment is a representation of space and time vectors, no, a dyadic product of space and time vectors. Okay? Okay, and then you have objects. These are all objects of second order. I say objects of second order matrices, which are represented by matrices, obviously. Objects of second order, which are R and S times NT. So you have delta US, dyadic delta UT, you have delta U1, plus delta US, dyadic delta UT, delta U2, plus and so on until we find our convergence. So this was the displacement increment in space-time representation. Let's go to the next thing. Space-time stiffness is not so straightforward, especially for how to put it, in a continuous framework is not so straightforward. In continuous framework, it's called a kernel, and here it's an object of third order. I can also say a kernel. That K, the object K with third order, is a dyadic product of a space stiffness matrix times its time stiffness vector. And this time stiffness vector is not trivial. It's that this is a vector is not trivial, and it's also controversial because other people from France, for example, claim that the time stiffness matrix is that the time stiffness can also be represented by a T times T matrix and not a vector. However, in our paper, we have proven that in our formulation, this can be represented by a vector. So is the sum of space stiffness, the dyadic product with space vectors, is an object of third order, which is an object of ns times ns times nt. It's a cube. No, it's not a cube. It has a certain length. It's okay, numerically. But again, this is just to imagine what's going on, because numerically, I will show you that we perhaps don't need all this. I mean, we need to formulate it, but we can use certain tricks to make it more efficient. And not these cubes are generally very expensive in space. My thing always goes forward on itself. I don't know why. Okay. Okay, let's go forward. So we have the stiffness matrix, we have the K times delta U, we have the incremental displacement, and now let's look at the residual using singular value. The residual R. The residual in a space-time formulation is, of course, also certain residual vectors at different time instants. Using certain as a residual matrix or residual object of second order, which is represented by a matrix, you have then the space residual times a certain singular value matrix times the time residual. So what do? We use the singular value decomposition, to decompose into ns times ns objects. So ns is the number of degrees of freedom in space, and nt times nt object, which means object in time. Reduce it. So you can rewrite this as an S times an S matrix and T times an T matrix and a diagonal rectangular matrix. So if you're interested in this singular value decomposition, let's see, it says a more general form of the eigenvalue decomposition. So you have Rs, dyadic Rt then in vectors as a sum of all singular values, which is equivalent to this matrix formulation. But as you see, it brings us our space-time decomposition of the residual. So it goes itself again. So the conventional equation of equilibrium, just to remind you, was K times delta U is F minus F internal is equal to the residual. And the space-time equivalent of this is inserting the few terms we developed before, which means Ks divided Kt, delta Us divided delta Ut, and the space-time residual. And instead of going incremental time by time, we have a space-time set of equations with motion. Okay, now let's go forward. Good. Of course, you're not calculating with this because this equation of motion is of order 3. Yeah, it's of order 3. No, it's not. It's of order 2. Yeah. But you want to get rid of this term. So in order to do this, you use a certain rule. Then you can calculate the periodic product here. If you're interested in rule how to calculate, go from here to here. It's not that complicated, but it's in our paper. And the right side, you have the residual formulation. Now what we do now is we transform, because we don't want an equation of order 2. You need Krylov-based solvers to solve this problem and so on, which you're also working on right now. But this equation is transformed into space and transformed into time. So projected into space, and projected into time, which gives me the blue equation is kind of a space equation, and the red equation, which is a time equation. Okay, so we have projected equations, and let's go forward. So we have two coupled space-time equations. The blue one is the space, the red one is the time. Yeah, and that's the important point. They are coupled. Of course they are. A system time instance, it matters what happened the time instant before. So the systems at certain time instance are coupled, of course. And this is a system of two equations you have to solve. So let's do that. Let's solve that. And we're not using the Newton-Raphson algorithm because we're using a different algorithm. We use the fixed point algorithm. So let's look at the solution here. This is a one-dimensional representation as illustration. So the blue curve is the space curve, and the red curve is a time curve. And where the two match, where the two intersect, we have our space-time solution of the problem, which is then the solution of the problem. I just call it space-time because it's space-time method. Okay. What do we do now is use the fixed point algorithm, which turns out to be extremely effective. We start from a certain point, ut, okay, which is here. Then I fixed a certain point ut, so I go into equation 1 and calculate us, solving this linear equation. Okay, so furthermore, now I fix us and calculate ut, so then I will solve the red equation. Then again, I fix ut again and solve us and solve the blue equation and so on and so on. And so you see here, for example, it converges within 1, 2, 3, 4 steps, which is actually realistic. For elastic problems, the modes, the space and time modes, us and ut, are validated generally within the first three iterations. Okay. What's the convergence criterion? The convergence criterion is also equivalent to the incremental formulation. You just calculate the mistake you make, so the error you make. This is the equation, and the error you make must be smaller than a certain value, certain positive value. Okay, so that you fulfill your convergence criterion. And then after you fulfilled the convergence criterion, then you converged for the first two modes, and then you update your system with the already obtained solution, delta us, delta ut is some of them, plus the enrichment of the solution on the right side. So we enrich the solution. So this is mechanical research communications, this algorithm. Okay. An illustrative example. I said we love the frame structures and going on with them because it's very simple. You have everything in it you need to test the systems for nonlinear, the test problems for nonlinear systems. We have an Euler Bernoulli beam element. We also implemented other beam elements by now, geometric and nonlinear, but this is another story. This is a certain, we are elastoplastic, so we follow a certain history in anticipation that we know already that something will happen, that a certain elasticity will happen. So it increases, decreases, and increases again. And hopefully we will have plastification. Of course, we will have to take care of that, but yeah, then we have a certain Gauss integration points, and in these Gauss integration points, you solve the material law. Okay, so this is the solution of the enrichments. Okay, so you see that there's a certain linear range, which is in white, and a certain nonlinear range, which is blue and red. Okay, so in a nonlinear range, you see in the linear range, you see that there's almost nothing happening. But in a nonlinear range, the iteration matters. Okay, so what you see is the development of the modes with increasing enrichment, and you see that, for example, M2, M5, and so on converge to the system very fast. The problem of elastoplasticity seems to be mostly in the temporal scale. There's the problem of time history and everything, and there is the whole action is happening there. There's not that much happening in the space direction. Okay, of course, there you see here, you will see here already some kind of elastoplastic deformation in the kinematics of the system, but the most action is happening here in the time scale regarding to elastoplasticity. Okay, we will talk about dynamics later. And this is the solution function. You have a linear solution curve. Let's say you have a linear system, then you have also a linear response then, which is the first enrichment as shown here by this red curve. First enrichment. And also in the first enrichment, you see here that you are walking in the linear scale. Then with the next and next enrichment, the system evolves. And generally after 10 enrichments, or see here, or 17 enrichments here, the solution is converged quite properly. Keep in mind we have 2000 time steps, and otherwise in every time step we need with a Newton-Raphson algorithm already 20, 30 iterations sometimes. Depends on how much plasticity occurs. Okay, so the point before the last point now. Elastodynamic spacetime solutions, we have the Newmark time discretization of the linear damp problem. We had a discussion about the Newmark equations. We have the equation of motion again, and we have the Newmark ansatz function. I brought them before, just to remind you, those are the three equations we need. What we have to do now is we have to transform an increment in time into a space-time increment, which means we have the blue vector, which has a matrix representation by the blue box here, and we have the green vector, which has a matrix representation by the green box. So we say the blue minus the green box. So we have a time overlap here a little bit. So in this time overlap can be fixed with this little trick that we have US, the dyadic, UT, with a certain component matrix that takes care of the sliding of the two boxes. And these are the initial conditions. Okay, and the initial conditions means that U0 is a certain A0 is not equal to 0 for only one component of this vector, which is the first one. Okay, now we use this strategy to transform the whole incremental system into space-time equivalence. Look at them. You transform this part here into space-time equivalent. You transform this here, yellow, green, and black. Okay? And then you derive from this the Newmark space-time formulations in second order equations. People say tensor order equation. I don't like it that much because yeah, it's not really tensors, but yeah, it's numerical tensors. Yeah. Second order equations, the Newmark space-time formulation, 3 equations, and these 3 equations, as same as for the incremental form, are now divided into a space-time form. Okay, so you have k times u times c times u times w, and this y and this w are go for the space-time shift. Okay. Now we have our space-time decomposition ansatz. So we have the sum here, which is the already calculated solution from before in the algorithm, and this is the new one, the displacement m. So and now it's gonna get a little bit uglier because equations are a little bit longer. You insert this into the space-time equation of motion. And you have here already the force term. The force term has also to be decomposed into space and time. You see it here. But it's a little bit uglier, but it's the same procedure as before the quasi-static problem. This is why it's so beautiful. You project this equation into space and to time, and then you have a space equation and a time equation, which you get here, which leads to the solution, of linear equations. And again, we're not using any Newton-Raphson algorithm. No, we use the fixed point algorithm, which converges, as shown before, converges very, very fast. And now I'll show you an illustrative example of how it's done. First of all, I want to emphasize that there are 3 examples in a paper we published a few weeks ago, which is computational mechanics. It's harmonic excitation, transient excitation, and so harmonic and transient excitation from the ground, and certain impact type of excitation at this point here. You have, because of reason of time, I'm not showing you all the results. You can look it up in the paper. I show you the results that work the worst for this method, that are the most inconvenient problem for this whole method, which is the impact. Okay, I'll show you this example now, and I will show you that already there is a very good convergence for this example. For the other ones, the convergence is even better. You can look it up in the paper if you want to. So the illustrative examples you see here, with increasing number of enrichments, we have certain space and time functions of this problem with which the solution is enriched. The first 4 solutions here. Okay. And then you see here, of course, you have the displacement of this node here, which is the red X, the red cross. And the vertical displacement is plotted here. The black line is the incremental solution, and the blue line is the space-time solution. Okay, and you see already that it converges quite well after 15 enrichments. There's not really anything happening anymore in the space-time solution. Okay. So even in the worst case scenario, which I think is the worst case scenario until now, the space-time solution works very well in structural dynamic framework. A small recap of space-time integration schemes. Space-time formulations are for non-quasi-static problems we have presented. The mechanical problem is described by 2 coupled space-time equations, which are solved by the fixed point algorithm, as I already said. And using is, if you know a lot of model order reduction, then you know you need generally a priori system identifications, singular value decompositions, and you have to know quite. That's the ironic thing, is you have to know already how the system will behave in order to reduce it, which is crazy, but it's the way it is right now. Huh? So for this method, that's not the case. This is why I wanted to present you this method, because it seems to work stable and for a lot of problems. So no a priori identifications as you're using model order reduction approach. And I didn't say this before, the Newmark algorithm is very, very effective. But the spacetime algorithm shows an is of course the speed up is dependent on the enrichments, how many you use, but for the problem above, I don't know, you have a speed up of factor of about 2 or 3 for the linear problem compared with Newmark. Newmark compared with Newmark, not even nonlinear problem. Nonlinear problem, they think that the speed up is even much better. You would say yes, perhaps the speed ups here for normal model reduction methods are higher sometimes. The PUD has speed ups until 100 or something, but you need the a priori system identification. So finally, we are now extending the system to nonlinear, so the space-time system to non-dynamic problems, which is now our current research about this. So finally, I want also, because I promised that, I want to, this was a very nice method from, it's not classical model order reduction, but model order reduction with a certain physical motivation. And it seems to me that the world goes a little bit away from physical and is a little bit more interested in data information, because there are quite fancy methods that you can do with data. So I want to also present you a few, one approach. We've published more, but that's more than that, but one approach that deals with data. And I want to publish this approach because I think here the data-driven strategy really makes sense. Sometimes they don't really make sense because you need already data to train, for example, a neural network. So you have to have the solution of the system already, So here, I think that in an America's way, it makes sense. What I think. Okay. I want to introduce to you the meta modeling of systems using the Monte Carlo simulations. So this is the first motivation, where to apply it. Yeah, the Carlo simulation now. We can also apply it to speed up numerical problems and so on. However, this is too much for the lecture here, but let me explain this, and you can find the rest in the papers in Google Scholar or something that's from our team. So where to apply for Monte Carlo simulation and why? Because it can actually speed up the Monte Carlo simulation from a practical engineering point of view. And that's not, a lot of people say you can speed up neural networks so fast. Yeah, they are fast when they are trained, and training them is an expensive procedure. So actually, you can already say they're necessarily not much faster than the normal procedure, and they're more inaccurate. It's always this discussion, and there's a lot of papers written right now. However, you always have this burden for practical applications, and this is where I want to use it now. So we want to present a neural network enhanced Monte Carlo simulation, and then I give you a link. And for this, we generate earthquakes, as you see here, artificially, and excite the structure. So let's look at the problem of earthquake engineering and structural failure. The problem of nonlinearity is really bad in earthquake engineering because you don't know what happens next. You don't know nonlinear systems cannot tell you what will happen in the future. You have to integrate it numerically. You have to do the hardcore integrating procedure. So, for example, let's see one earthquake here, and it results in no damage to the structure. We are happy, everything okay. Let's look at another earthquake here with certain intensity, let's say a magnitude of 7, and you have certain cracks in the structure. Let's take another earthquake at the same intensity of 7, same intensity, and it breaks down. The problem is the damage of cantilever structures is nonlinear, and you have to integrate numerically to give an answer. This is the big problem, and the probability of failure of a certain structure for nonlinear systems is also a big issue, which is actually not solved by now. Only solved by one method, which is the Monte Carlo method. Monte Carlo method means you try it that often that the structure fails a few times and it doesn't fail, and then you count the times when it failed, and this gives the probability of failure. Okay, so I will repeat this again. So just a little bit of probabilistic now, a little bit just. This is the probability of failure. Is the integral? No, this is not the probability of failure. This is the probability of failure already by Monte Carlo simulation. Is the integral of certain indication functions over the whole domain of the system. So the Monte Carlo method, as already, well, what this integral says is, if I want to know how the probability of structural failure is, I calculate 1,000 random simulations. The structure failed 200 times. Then the probability of failure is 200 over 1,000, which is 1 over 5 is 10 to 20%. And now we come already to the problem. So what did I do now? What did I do? I did nothing else than calculating the estimation of the probability of failure. I calculated the probability of failure in terms of an estimated value. This is the Monte Carlo simulation, okay, in terms of an estimated value. So I said, yeah, the probability is 1 over 5 because I did 1,000 experiments. And now we are already coming to the big issue of the Monte Carlo simulation. In engineering, we want structures to fail very rarely. We want to fail them rarely. So let's say from 1,000 samples, we want to fail them at 0 times. So we need to calculate 100,000 samples to say, now at 100,000 samples, we want it to fail 10 times. Okay. So you need to calculate 100,000 samples to calculate the probability of failure of, let's say, 0.10 to the power of minus 4. Okay. So the problem is here. This, what you see here, this is the limit state function. Everything above the limit state function is failure. Everything below the limit state function is safe. Only one sample here failed. So the confidence of the estimate is very low. So you need a lot of samples in order to estimate the probability of failure with high confidence, which means very certain. Okay. So, finally, I want to talk about this is numerically feasible, but it doesn't give us any result. This is numerically unfeasible, but it could give us a result. The idea now is to take a certain initial sample set using neural networks, initial sample set, that's to expand to excite the system with more extreme events, so that the neural network also learns the behavior around there. Okay, the neural also learns the behavior around there, so that we finally can do this calculation very fast. So what we actually do is, when the neural network is very good, neural network is what is it? It's curve fitting. It's fitting the system to a certain quite complex structure of matrices. Yeah, this is what it is. Okay. So what do we do now? First, this is something technical about structural dynamics. you have a certain excitation function, which is your benchmark excitation function, and then you go with a window over it and screen it, and screen the properties of these excitation functions. And you get the properties here, polynomial fit. Okay, then you have a certain intensity here that increases and decreases again, and then you have a certain frequency range of earthquakes with time. And this we use to calculate artificial ground excitations, which means we're using a nonlinear filter, and the nonlinear filter, which is represented by a nonlinear single degree of freedom system, and this is excited by a Gaussian random white noise. And the solution of that, the acceleration of the solution of that, gives you an artificial earthquake that has similar properties, but not exactly the same property as this one. So what we're doing is still Gaussian statistics. Gaussian statistics. Here you see, for example, one numerical example. You have a structure, you have a ground excitation, and then it vibrates somehow. And then one important thing you calculate is the peak story drift ratio. This is the ratio how much the peak here, mostly it's the first one, how much this goes to the side. And then you see the story drift here with time. And then you see that the first story weirdly stays to the side. And there are certain pictures, if you Google earthquake damage to structures and on, they tend to stay like this afterwards. So there was severe damage. In this case, there's severe damage. You can throw it out afterwards, the building. You can, get rid of it. There is no way you are repairing such a building. Okay. So the strategy is we have a structure, we have a certain amount of excitation functions, that's the Monte Carlo method. We evaluate all the response sets to these excitation functions. We calculate the peak story drift ratio, which is the example of the vibration, and then the probability of failure. It is, of course, not feasible, especially for this structure, perhaps yes, but for real engineering structures where you have a lot of degrees of freedom and nonlinear probabilities, it's not feasible, especially if you have 100,000 earthquakes to go through. We talked about this before. This is numerically not possible or very hard. So this is very bad. So it takes a lot of time, and we need a lot of calculators, a lot of guys who calculate here. So what we are doing now is the green box is a training procedure, and the red box is the prediction procedure. The training procedure is when a small initial sample set helps us to calculate the response functions and the output functions and train a neural network with these functions. And after this initial sample set is finished, if it's trained enough, and you can say, yeah, in neural networks, you have certain procedures, you have a training strategy, then you have validation and test sets. And when the test set is fine, then you say, okay, my neural network seems to work well. And now I'm going with all the number crunching and all the high, all the data goes with the neural network, and we predict the PSDR then and get the probability of failure. Okay. Here is the result. Here you see the peak story drift ratio as a histogram or as the probability density function. And you see that the peak is around here, about 0.02, and the real one is the full Monte Carlo simulation is the black dashed line, and the classical training is the neural network. But there's one problem. Engineers are not interested in this range. Engineers are interested in this range, which is the range where the action happens, where it decides the structure fails or it doesn't. So look here. So you have the full the Carlo simulation set, and we have a probability of failure of 10 to the power of -3. Okay, for a story drift ratio of 4.5 centimeters, which is quite realistic. Okay. But the neural network fails, of course. It didn't see the data. It doesn't know what to do up there. So the neural network says everything is fine. And that's the problem. That's the problem. Neural networks don't have the amount of creativity that's necessary to extrapolate data very well. So what to do? We have a good results about the mean region, which is fine, perhaps for structural maintenance and everything. It's okay, yeah. But for the nonlinear range, or for the range that's really of interest, we have a problem. What are we doing? We use an extended strategy, training the neural network by an extended special set. Extended so the neural network sees more, it learns new things. Then you see the results here. In the first side, it's bad because you see the extended set doesn't know the mean so well anymore. The mean region of the distribution, it's okay, it's approximately the same, but however, it's not so important. The neural network is very well in the tail end of the distribution. The tail end of the distribution is the important thing in structural engineering. So it means that the classical training, and then you have now the neural network extended training that really can predict accurately the probability of failure for very small probabilities, the probability of failure for very rare events. So we have an improved results around the region of failure, but the mean region is not that well, but this doesn't matter so well, okay? What matters is the tail end of the distribution for failure computation. So now a little bit about the neural networks. What do? We have we have to classify or to describe certain excitation functions. You have acceleration, velocity, and amplitude in terms of intensities. And then you have intensity measures, which are the input into our fully connected neural network problem. You can look this up. It's a feed-forward neural network, and the output is the peak storage ratio. So the simple neural network. I'm not using any complicated neural network architecture because this is not, in my opinion, here. I want you to concentrate on the method as well. And using a more complex neural network architecture is not a secret. You can use TensorFlow and you can use whatever you want, neural net and NarcSnet and whatever, different neural networks. It's now the strategy here that you have a simple neural network is sufficient to do this thing, and it is extremely fast if you have 20 layers, okay? And then in the end, you have here a second neural network that's a little bit more complex, a convolutional layer, where the hand-chosen intensity measures are not necessary anymore. So the neural network chooses this value itself and calculates the PSDR with that. So a little bit more complicated neural network, a convolutional neural network that does the job well as well. So we have improved neural network architectures. We have high quality data with several benchmark records, and we have sampling methods for the proposed strategy. I thank you very much now, and I'm very open, and I hope it wasn't too long. I'm very open to question now, and very excited about discussions. Thank you very much.
Dear participants, if you would like to ask questions to the resource person, you can do that. You can use even the chat window, please.
Chat window, wait, oh. Chat window.
Question is how to improve the results in the region of failure.
How do I prove the proof? What do you mean by proof?
Improve.
Okay. I have to go back. Okay. Yeah. let me put it this way here. So, you have, this is the problem, that the normal neural network does not work well to predict a structural failure, because it almost saw nothing around there. There was nothing it saw because we want failure to be happens very rare. Okay. What you do is you extend the range of data far into the region of failure, so that the neural network learns, okay, how to deal with it when it comes to that. And how do we do it? We creating, and this is important, we going over the earthquake and measuring certain intensity measures. And these intensity measures are multiplied by a certain Gaussian random factor. By including another higher variance for this Gaussian random factor for the intensity of earthquakes, which you see here, you see that the earthquake sample set spreads significantly. And this is, so technically the answer to your question is then, how do we do it? We increase the variance of the intensity factor of the extracted earthquake measurements. So the earthquake has still similar properties, but the intensity is a little bit changed. I hope I answered your question with that.
If there are any other questions, you can please raise on the chat box, please.
Sandeep, I don't see the chat box. Can you tell me if there is a question?
Till now there is no question, but yeah, if there is question, I'll tell you.
If there are no questions from the participant side, then we can share the contact details of the resource person with the permission of the resource person, Dr. Franz Baumer.
Of course.
Okay.
Yeah.
So the resource person has given his consent to share the email ID of the resource person, so that in case if you would like to raise any questions, you can directly contact the resource person. So without wasting much time, then we will conclude this session. So we once again would like to thank, on behalf of all the organizing institutions, the Rajiv Gandhi National Institute of Youth Development, Chennai, India, and the RWTH HN University. We would like to profusely thank Dr. Franz Baumer, the group leader of the Institute of General Mechanics, RWTH HN University, Germany, for facilitating this wonderful lecture on model order reduction and efficient meta modeling in structural mechanics. We thank you very much, sir, for sparing your very valuable time and for delivering this excellent lecture. We do hope
I thank you for letting me talk. I thank you.
Welcome, sir. We do hope and trust that the participants would have found your insights very useful, and should they require any further support or clarification, they would contact you directly. Thank you, sir. And for the
Thanks.
kind, we also would like to thank Dr. Sandeep Patil, group leader from the Institute of General Mechanics, RWTH University, for his excellent coordination. Thank you very much, sir. Dear participants, we are going to close this lecture session for now. Tomorrow we will have this lecture session. The fourth speaker will be speaking on the multi-scale modeling of hierarchical biomaterials and advanced materials, which will be facilitated by Dr. Sandeep Patil, who is daily joining us and who is coordinating from the RWTH University side. So we request all the participants to make sure that your presence is available 15 minutes ahead of the commencement of this program. That is 1:30, the lecture would commence sharp Indian Standard Time. So we request you to log in and be positively present by 1:15 p.m. itself, so that we are ready for the next resource person tomorrow. Thank you so much. Till then, goodbye. Have a good day. Thank you very much, sir. Thank you, sir. Thank you very much. Thank you.